Hello students, welcome back. We are done with section 2, limit rules. Now let's go to section 3, limit computation. First, some trivial limits. These kind of problems, just plug in the numbers and hope for the best. And indeed, the best happened. In some cases, not the best but good enough. We got 8 over 0 undefined, but that happens to be the answer, so it's good. In some cases, however, we get only a partial solution. Log of 0 is undefined, so we have undefined, but that's not the end of the story. We have to do further, and we can do further. This is something we are going to come back and discuss in 3.4, so please be patient. In short, plugging in the numbers, do good, yes, but there's a limit to it. Sometimes we may have to improve it, and that's something we have to consider in 3.4. But in other cases, it worked out. Now, what about the kind of problems that you cannot plug in numbers at all? Like these. Plug in the numbers and you're going to get 0 over 0. Try it on your own. This too, 0 over 0. And that too. Another type, infinity over infinity type. Try these. All these are fractions, and these two are the most important types of limit problems. Excuse me, did I say the most important types of limit problems? No, that's not true. The most important types of limit problems, that category belongs to graph problems. Among the limit computation problems, these two are the most important. So I should have said these two are the most important classes of limit computation problems. Okay, one step at a time. First, a 0 over 0 type limit. Typical technique here is to factor the numerator and denominator. Factor those, and you'll see a common factor. And they happen to be the 0 factor, where x is approaching to 2, then x minus 2 goes to 0. So these red factors created the environment 0 over 0. But they're common in both numerator and denominator, so they just cross themselves out. Divide those out, and we get a new expression here, which is highlighted in blue right now. And that one is no longer 0 over 0. So we can plug in the numbers using those limit rules. And what do we have? We have 8. That's a solution. Not too bad, wasn't it? By the way, here is a wrong solution. Why is this wrong? After all, we have the same answer. But what makes this a wrong solution? Think about that. Stop the playback and think about it and tell me why. What's the difference between this and that? This one comes with limit, no LIM. That's the difference. What is a limit? Limit is a value. It's a y coordinate. For example, limit of x going to -4 is this y coordinate value. Follow the graph, this y coordinate value. So limit is y coordinate value. Sometimes we have positive or negative infinities, so it can be a extended real number, but still it's a number. And here, this is a number too, so all is okay. Left hand side is a number, right hand side is a number, no problem. Now look at the wrong solution here. Right hand side is a number, but the left hand side is an x expression. The left hand side is a function. Right hand side is a number. They are not the same. So without the limit, without this limit expression, we do not have the right solution. If you do it like this, you're going to lose a couple of credits, I guess. 8 out of 10, that sounds reasonable. If I'm in bad mood, maybe 7 out of 10. And if you miss something further, like some equalities or those other symbols, then it can go down even further to 5 out of 10. So in any case, make sure you use correct mathematical grammar. You see, this is mathematical writing. So just like any writing, you have to follow appropriate grammar. And in this particular case, grammatical rules are, well, equalities are always important, but also the limit. Limit expressions are important. Whenever you have x, limit stays. No x, then you don't need limit. Limit x is going to 2, and the moment you plug in x equal to 2, you don't need limit. Before that, you have to have limit. Okay, how about the next problem here? Well, looks like this problem is more intimidating because we have much more complicated figures, but still, you can factor these. Factor the numerator and factor the denominator, and look for the common factor. Here's a hint. X is going to 2/3, so the common factor must be 3x minus 2 must be a common factor. You see, this one goes to 0 when x goes to 2/3. If you plug in x equal to 2/3 and do your computation, you're going to get 0 over 0. If you actually factor it, then this is your computation. You see, you have 3x minus 2 here, and 3x minus 2 there. These two divide themselves out, and what's left is this expression here, highlighted in blue. And from here, you can just plug in the numbers and do your computation, because this is no longer 0 over 0 type. You have many more problems like this in homework set, so I'm not really worried. Now, how about these? Now, these are a bit more challenging because you cannot factor it directly. But frankly, I'm not going to be worried too much at this moment because there are much better tools to handle this kind of limits. L'Hopital's rule that we're going to learn a couple of weeks later. And if you use L'Hopital's rule, then this becomes a bit tedious but elementary problem. But if you want to find out the solution that you can do right now, right here, well, here it is. You can multiply the conjugate of the square root expression to both the numerator and denominator, and then do your algebraic manipulation. With some difficulty, you'll be able to do all those computations, and eventually this h and that h cancel each other out, and you're going to get this limit, which is no longer 0 over 0 type limit. So you can plug in the numbers, and if you do, you're going to get the answer. The key is, of course, to do this, and then following through some algebraic manipulation that comes with it. That's going to be tedious, really tedious. So it's going to be probably better with L'Hopital's rule. Okay, so much for 0 over 0 type limits. And next I have infinity over infinity type limits, but this is going to be a longer topic, so I'd much rather do this in a second video. So instead, let's take a bit of time to talk about this example, 3.4, one-sided limits. One-sided limits come with graphs. For example, this kind of problem, if you plug in x equals to 3, you're going to get not 0 over 0, but you're going to get something else over 0. Let's see if I plug in x equals 3. By the way, a little bit bigger font will help. So 9, and then another 9 plus 2, so we're going to get 20. 20 over 0. So can we just say undefined and walk away? I can't do that because this is going to 3 minus. Do you see that 3 minus here? Maybe even bigger font. Is that clear now? 3 minus. So for one-sided limits, just plugging in the numbers will not cut it. How do you handle it? There are two ways to handle this. and my preference is to use graph. Look at the graph and follow the graph from the left-hand side because this is 3 minus. And clearly you can see that y-coordinate is going down to negative infinity. That's the answer. Algebraically, it works like this. This is going to 20, and that's going to 6. Both are positive. And x minus 3, that's going to 0, but 0 minus, because this is 3 minus. Close to 0, but a little bit to the negative. So what do we have? Negative infinity. Hard to understand. Easy to understand. Which is better? Make your choice. This is what you get if you have limit from 3 plus from the right hand side. You can use the same idea using all the signs, or you can use a graph going up to positive infinity from the right. How about the next problem? Well, stop the playback and draw the graph and tell me. So, are you getting the answer? Are you getting 0? Here's a graph, and if I follow the graph from the left-hand side to 0, the graph is going down to negative infinity. From the right, staying constantly at 0. Why is that? That's because this absolute value is equivalent to negative x, because you see x is getting closer and closer to 0, but a little bit less than 0 because this is 0 minus. So how do you make it positive? By putting extra negative on there. So what do we have? 1 over x minus 1 over negative x, so 2 over x. So you end up with basically 2 over 0 minus. Yeah, so that's negative infinity. You see, something over 0, so the absolute value, the number part is blowing up to infinity, but it's negative side. And if you approach from the right hand side, then absolute value and x has no difference. So we have 1 over x minus 1 over x, so that's 0. But then again, look at the graph. The graph tells you everything. How about this problem? Again, look at the graph. That's the incomplete solution. We cannot simply see undefined. Log of 0 plus, well, graph of log function looks like this. Kind of like this. So if I approach x equal to 0 from the right hand side, y-coordinate is going down, 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 down to negative infinity. So the numerator is going to negative infinity. Without the log function, you can still answer this problem simply by graphing the entire function there, like this. If you do that, you can clearly see that the y-coordinate is going down to negative infinity, either way, from the positive direction or negative direction. Even though this problem started off as just usual limit, not one-sided limit, we ended up with one-sided limit as an intermediate step. This can be a bit tricky, but in any case, graphs would certainly help. So unless you have some typical problems that you can handle with factorization or some other alternative method, drawing a graph is always helpful. As a matter of fact, drawing a graph is always helpful, period. No matter what.